Hello, Math 8 students. This is a brief introduction to geometric transformations. We're going to be talking about three different transformations today. We call them rigid transformations, and we'll explain a little bit more why we call them rigid transformations, but the rigid transformations include translation, reflection, and rotation. I'm going to demonstrate each one of them, and I want you to try and come up with a non-mathematical word that will help you understand and remember what these three transformations mean. The first one is translation. Watch as I perform a translation. See if you can come up with a word that describes what's happening. There's a translation. There's a translation. And this is a translation. A non-mathematical word that represents what you just saw is slide. I was simply sliding that figure across the paper. The next one is reflection. It's a little bit harder to demonstrate, so bear with me. Here's my figure. I'm going to perform a reflection. There we go. There's the reflection. What happened? Let's do another one. A word that we could use to describe reflection is a flip. Reflections, when performed correctly, require something specific, and they require a line to reflect over. That line to reflect over is called the line of reflection. Just like you, the only way that you can see your own reflection is if you have a mirror in front of you. This line of reflection acts like that mirror. So here is the image. Here's the line of reflection. Notice the distance between the triangle and that line of reflection. When I perform the reflection, it's going to flip over that line, but again, remember how far away it is. As I reflect it, it stays that same distance, but is flipped to the other side. So a reflection requires a line of reflection. If I wanted to make that look different or have it end up in a different spot, I just need to alter that line of reflection. Now as I perform this flip, it's going to end up on this side, and that would be a reflection. The next one that we're going to talk about is a rotation. Watch as I perform a rotation. Here's a different rotation. How can you describe what's happening there? I think a good word to use would be a turn, or I like the word twist. Rotations also require some specific information. It requires a degree of rotation. I need to know how much to rotate. For example, this is a 90-degree rotation. Look at where I'm starting and look at where I'm ending. That's a 90-degree rotation. Let's start over. Now I'm going to do 180 degrees of rotation. Notice that they ended up in a different place because I rotated different amounts. This is also where the concept, the skateboard trick of a 360 comes from, because I'm rotating it 360 degrees. I'm turning it all the way around. In addition to needing a degree of rotation, rotations also require a center of rotation. This one's a little bit harder to demonstrate, but we will do it a little bit later. Here is a center of rotation with my finger being the center of rotation, or this corner of the triangle being the center. Notice how it doesn't move much. In fact, this point stayed exactly the same. But if I change that center of rotation and I attempt to rotate it around this point, now that triangle rotates a little bit different, and every single one of those points switched into a new position. So that center of rotation has a lot to do with where the triangle ends up. We're going to be looking at page 450 from your books and performing those hands-on activities. On page 450, we have a right angle on some tracing paper. I'm going to be performing a reflection, and so I'm going to be reflecting it over. Do you see this line of reflection? I'm going to be flipping it over that line. So with the tracing paper, I can simply fold it over that line and now it is reflected. Because it's tracing paper, well, when I open it up you can see it's not there, but because it's tracing paper, I can just trace it onto the other side, so bear with me as I get that done. Okay, let's go back to that original. And you can see that it's kind of hard to tell which one is the original and which one is the new one. And so that gets us into some new terminology that I want to discuss. The pre-image is the original image. After we transform it, whether we're performing a reflection, rotation, or translation, we create an image. The image is the new one. It might be difficult to try and remember this new vocabulary. Just remember that when we have a pre-game, it has to happen before the game, just like the pre-image has to happen before the image. The prequel of a story happens before the quel. So pre means before, that makes it the original. The image is the new transformed figure. So going back to this is the pre-image. And this is the image. When we have our pre-image and our image, this is labeled Z, so I can't label this one Z because it's not part of the pre-image. But it's Z that has been reflected. So we also have a naming system that we can use. Instead of calling it Z, I'm going to call it Z prime. Notice it's a Z with what looks like an apostrophe, Z prime. Just like this Y is reflected and is now this point. So that is going to be Y prime because it's part of the image. And X, when it's reflected down, is down here and is going to be called X prime. Now that we've done those, I want to actually demonstrate the cool things that happen when we're doing these rigid transformations. This is our reflection. Notice that we already have it as a 90-degree angle, but when I have reflected it, I want to measure that angle to see what we get. So I'm lining up my protractor, lined up down here on the bottom with that line, and now this is going to line up here with this line, and I can see that it is a 90-degree angle. So it kept the angle. This was 90 degrees, and this is also 90 degrees. The other thing that's cool about these reflections and other rigid transformations is I'm going to measure from Y to Z. From Y to Z, you can see, is 3 centimeters. Let's measure from Y prime to Z prime, and you will see that it is also 3 centimeters. So it preserves the distance between points as well. Now let's move on and explore a rotation. This is also on page 450 of your books, although I'm going to be doing it just a little bit differently than it demonstrates in your book. Here you can see I've got 2 pieces of tracing paper, and I've just traced that same trapezoid onto both. I'm going to perform these 2 rotations. Here's the original. There we go. Here's the original, but as I rotate about this point X, look at how it changes. Notice that it still has X in common in both of those figures. Now let's go back to the original. I'm going to choose a new rotation point. I'm going to rotate it through this one. Okay, they line up. Now I'm going to be rotating. Look at how it's in a completely different position than it was during that first rotation. Still rotated at 90 degrees, but now I've rotated at 90 degrees about a different point. Compare this new image to the original. Did it change shape? Did it change size? Obviously not, since I traced them to be the same size. I simply just rotated it. So the size didn't change. It's a trapezoid here and it's a trapezoid here. So rotations will preserve that shape, just like we saw with the reflection preserving our line segment length and the angle. We're seeing that these are going to preserve the shape as well. To further explore this, I have a line. I'm going to translate this line. Let's see what it becomes. Translated, looks like it's still a line. Let's try a reflection. In order to do a reflection, remember, I have to have a line to reflect it over. So here's my reflection line, here's the original line. What happens as I do that reflection? It's still a line. And what if I do a rotation with this line? Let's rotate it, and guess what? This line is still a line. I know it seems really obvious, but these are the foundations to understanding all of the other geometry concepts. Lines are taken to lines. When it's a line, it still is a line even after it's been reflected, rotated, or translated. What about this angle? You can see that this angle, I can't bend it, I can't change it. So here's an angle. What happens when I translate the angle? Still is the exact same angle. What if I reflect this angle? So again, let's get that line of reflection. What if I have that angle and I reflect it? Is it going to change? It might have changed the position, but the actual measure of the angle can't change because, again, I can't bend it. It's rigid. And what about a rotation? Did the angle change? It might have changed its location, but it didn't actually change the measure of that angle. And finally, here you can see I have parallel lines. What if I take these parallel lines and I translate those parallel lines? Will they still be parallel? Looks like it. What if I take those lines and I reflect it? Now this one's going to be a little bit harder to demonstrate because you won't be able to see them anymore. But use your imagination here. If I do that reflection, is it really going to change those lines? They're still going to be parallel. What if I rotate them? Those parallel lines are still parallel. They may not be parallel to the original set of lines, but they are parallel to each other. And that's what really matters. So that gets us to, again, that main concept of rigid transformations. They're called rigid transformations because length and angle measure are preserved, which means that they just stay the same. Length and angle measure are preserved. That means when I perform a translation, reflection, or rotation, it's going to be the same shape and the same size. It might just be in a different position. That's it for your introduction on rigid transformations. We'll be exploring these transformations a little bit more in the coming days. Thanks so much, folks. Have a good one. We'll see you next time.